Hello again. We are finishing up our discussion of differential equations by talking about how to approximate solutions to differential equations. There's three methods that we're going to talk about. The first of those is called slope fields. So let's say I have a differential equation. It looks like this. dy dx equals x minus y squared plus 2. What I can do is I can find a whole bunch of tangent slopes at different points. I can use a bunch of x's and y's that are points that might or might not be on the graph and figure out what the slopes would be at those points. So for example, if I wanted to see what the slope at 0, 0 would be, I would plug in 0 for x, 0 for y, and I would get a slope of 2. If I wanted to know what the slope might be at -1 and 2, I replace every x with -1, every y with 2, and I get a value of -3. And I can keep doing this for a bunch of points that may or may not be on the actual graph. And then when I do that, I can make a table. And the two values that I figured out ahead of time are already there in the table, and I've highlighted them for you so that you see where they go. All right. And so once I've got that table done, what I can do is I can make a graph and I can find each of those points on the graph and just make a little segment that has that slope at each of the points. So you'll see there that I've got 25 little segments on there to represent the 25 points that I looked at and found the slopes for. All right. So what I can do is I can start anywhere I want and I can sketch approximate solution curves, just kind of following the little slopes at each of the little points and see what I can do. The two rules of doing this are when I'm drawing a bunch of curves, I've got to follow the directions of the tangents at each point, and I can't let the curves cross each other. So those are the only two rules. So that's one possible curve that the function could be, that y could be. Here's another one that y could be. Here's a third one and a fourth one. So I don't know which one of them it is. I would need a boundary condition in order to do that. But here's just a family of curves that has that differential equation as a solution to the actual curve. All right. We could also use isolines in order to help us draw these curves better. And what those are is those are curves on which all of the points on that curve in a slope field have the same slope. So what we can do is we can set dy dx to different values and draw each little isoline for each of the values that dy dx could equal. So if I set dyx equal to -1, then I have x minus y squared plus 2 equals -1, and that's the sideways parabola that represents that curve. If I had x minus y squared plus 2 equals 0, it would be that curve. And if I had x minus y squared plus 2 equals 1, it would be that curve. And so I have three curves. It doesn't have to be any of those three curves. It could be any curve that is of the form x minus y squared plus 2 equals some constant. So I draw as many as I can. And then it makes it a lot easier to draw the tangent segments on each of those isolines. And from there, I can draw possible curves that could represent the y function. All right. All right. The second method I'm going to talk about is Euler's method. So if I had a starting point, x naught and y naught, then what I could do is I could use successive slopes and points to approximate the curve. So first I'm going to make a table that looks like this. I'm going to use x's and y's in the first two columns. I'm going to use the dy dx as my m function, my slope of a line function. And then I'm going to change my x by a little bit, and I'm going to change my y according to what the slope is, and find another point, and then another point, and then another point. So we're starting at 0, 1, since I know that that is on the curve. I'm just saying that I know that that's a point. And I want to know whereabouts would the y value be if x was equal to 1. So I'm going to start at 0, and my x's are going to go up by 0.25. So that's going to be my change in x. So I start at 0, 1, and I figure out that the slope of the tangent line at that point is going to be 1. So if I go up by 0.25 in the x direction, I'm also going to go up by 0.25 in the y direction, maintaining a slope of 1. So that gets me to the point 0.25 and 1.25. That's how much my x changed, and that's how much my y changed. So now I'm at that point, 0.25 and 1.25. So again, I plug those into my derivative function, which gets me a tangent line slope. And if I do that, my tangent line at that point has a slope of 0.6875. So again, my x will go up by 0.25. My y will go up by an amount that's equal to 0.6875 times that, which is 0.171875. So from this xy that I've got at the start of the row, my x is going to go up by another 0.25. My y is going to go up by that decimal right there. And where I will end up is my new x will be 0.5 and my new y will be 1.421875. So I plug those into my derivative function again, and at that point, the tangent line has a slope of 0.478271. So my x's will still go up by 0.25, but my y will go up by 0.25 times the new slope. And so it will go up by 0.119568. So adding that change in x and that change in y to the x and y that's at the start of the row, now my new x is 0.75 and my new y is 1.541443. I repeat that process, plug those into the dy dx function, and I get 0.373954. My x is still going to go up by 0.25. My y is going to go up by 0.25 times the new slope, and I'll get 0.093488. So changing x by that much, changing y by that much, now I'm at x equals 1, and my y value is 1.634931. From there, I don't need to figure out what dy dx is or what my change in x or change in y would be to get to the next point, because I'm where I want to be. I am at x equals 1. So all I need to do is look at the y value when x is equal to 1, and y is going to be approximately 1.634931. So I've answered the question. If you just want to see what the graph would look like, those are the points that I found, starting with x equals 0 and ending at y equals 1. So that's an approximation of what the actual curve looks like. But I don't know the equation of it. Then again, I don't need to. I just needed to know what approximately the y value would be when x is equal to 1. The third way to do this is to use Taylor polynomials. So I've got a differential equation that's a function of x and y, and then I've got a starting x and a starting y. So I can approximate a solution by making a Taylor polynomial for y about x naught. So remember, Taylor polynomials have all of those x minus a's in them. That a is going to be x naught, whatever the question tells me that function is. So there is the generic Taylor polynomial right there. As you can see, I would need to know what the y value is at that x. I would need to know what all the derivatives are for that x. And then I would need to do x minus that x to various exponents. So here's an example. I've got dy dx equals x squared plus y squared. I need to approximate it to degree 3, where y is 0 when x is 1. So I don't know what the y function is, but I do know that the derivative of it is x squared plus y squared. So taking the derivative of that, I will get 2x plus 2y times y prime. Taking the derivative of that, I get 2 plus product rule on the second term, giving me 2y prime plus 2y y double prime. And now let's plug in some of the values. So at 1, when x is 1, I'm told that y is equal to 0, so I don't need to calculate that. For the first derivative, I'm going to replace every x with 1 and every y with 0, giving me that the first derivative is 1. I'm going to need that to figure out the other derivatives. So for the second derivative, I'm going to replace every x with 1, every y with 0, and every y prime with 1, since that's what I figured out y prime to be equal to. So now I know the second derivative is 2, and I'm going to need that along with the first derivative value of 1 to figure out the third derivative at 1. So I'm going to replace every x with 1, every y with 0, every y prime with 1, and every y double prime with 2. And that's what I get. I get a value of 4. So now I'm ready to plug all of this information into the Taylor polynomial of degree 3. So I get 0 plus 1 times x minus 1 plus 2 over 2 factorial times x minus 1 squared plus 4 over 3 factorial times x minus 1 cubed. And if I simplify that, that's what I get. X minus 1 plus x minus 1 squared plus 2/3 x minus 1 cubed. Now I could simplify that, but if I'm just using it to approximate y values that are close to the x value I was given, then I really don't need to simplify it and collect like terms and all of that. I just need to plug in the x that I'm given and figure out what y would be equal to. So there's my Taylor polynomial. I'm looking for the value of y, or the approximate value of y, when x is equal to 1.1. So what I do is I replace every x with 1.1, and that's what I get. So it's all numbers now, so I can figure out what it is. Everything in parentheses is 0.1, and then if I simplify that even further, I get 0.1 plus 0.01 plus 0.006666, and so on. And if I add all those up, I get my final approximation of y, which is 0.1106666, and it keeps going like that. So those are three different methods of approximating differential equation solutions, finding y values of x's that are really close to a given x. A lot of information. We will go over all three of these tomorrow in class. And if you have any questions, please let me know, and I will see you tomorrow.